In this video, we're going to be talking literally about the nuts and bolts of aerospace engineering. That is the bolted joint design. Now, the first time I designed or was asked to design a bolted joint in an aerospace application, I really didn't know what I was doing. I wasn't sure what size should I use, what type of fastener should I use, what threads should we use, what materials, what finishes, etc. And there are a lot of considerations when it comes to aerospace applications that need to be addressed before you can select the proper fastener. So in this video, let's walk through the basics of designing a bolted joint for aerospace applications. So it was about 4 years into my aerospace career when I really got heavily involved with having to design structures that needed specialized bolted joint designs. And the very first time that we tried to build an assembly, a project with me and a few other engineers that were about the same age, fairly new to the industry, and we relied on the experience we gained while we were in college. In that case, we had built projects for our school, and we just picked up whatever fasteners we could find at the local hardware store. We may have used McMaster Carr in some cases if we couldn't find something locally, and that had sufficed for kind of an engineering project. But when it came to actually working in the industry, things get a lot more complicated. So first project I was working on, we had to design some equipment installations inside a crewed aircraft. And so we had to mount equipment in the cabin where the crew would be operating. And, that involves making sure that equipment would be not just mounted in there, but that under certain load conditions, that the equipment wouldn't come free and actually injure someone. We had to work through FAA requirements. In this case, it was a military program that was requiring us to follow FAA regulations. And so we had to work through how much load did this joint have to take to make sure that it didn't fail. Well, when we designed it, we fell back on our experience from college and ordered some fasteners from McMaster Carr, got all of our equipment racks together, got everything out onto the production floor, and our Air Force inspector from the government came over to see how we were doing, looked at the equipment that we had purchased and were trying to assemble, and said, that's just not going to do it. We can't do that. He explained to us kind of the background behind the kind of mistakes that we were making. And basically, we can't rely on a lot of that hardware that is just commercial off-the-shelf kind of equipment that you might buy at a hardware store. The sources may be unknown. The materials may have high variability. That the standards in which those fasteners are designed, manufactured, and tracked do not meet the aerospace standards. And so he very quickly helped us get a collection of aerospace grade hardware brought over from another facility, and we figured out what the right fasteners were to use for that application. And very quickly we started to realize, oh, there actually is a unique set of hardware that we have to be familiar with when it comes to designing aerospace vehicles. And so what I wanted to go through today is a little bit of what that background experience was for me and how I can help you to get ahead and understand what the aerospace fastener design requirements kind of look like, what specs are out there and available to you, and how you go about designing a very basic bolted joint design. So let's talk briefly about why aerospace fasteners are different perhaps than what you might see in other industries. In the aviation and space environment, we're typically operating in a harsh environment, right? The flying through the air at hundreds or thousands of miles per hour, altitudes that vary from sea level to tens of hundreds of thousands of feet in the air, where temperatures vary a lot, or all the way out into the vacuum of space, where the one side of the vehicle to the other could be hundreds of degrees different. You may be working on components that are working for a propulsion system, so rocket engines, jet engines. These experience extreme loads, temperatures, They're all having to operate in potentially corrosion susceptible environments for long periods of time. And so they may be carrying people, human beings, in which case, a failure of one of these fasteners could be catastrophic and lead to the loss of life. So depending on the exact application, there may be more or less required stringency on what fasteners you're selecting and how you're screening them and designing the joints that you're working on. But when it comes to fasteners in the aerospace, the main things that we're worried about are things like reliability in the fastener, which is how predictable are the material properties of that fastener. Is it made from a material that is going to have a good consistent behavior? Has the manufacturing process been implemented in such a way that we can ensure that the next bolt coming off the product line isn't defective? There's corrosion that we have to worry about in the environment, and so when fasteners, especially major structural fasteners, may be implemented in the field and used for decades, and you don't want them to corrode or crack. You also have to worry about things like fatigue, cycles on the airframes or vibrations during launch of a rocket or what have you. These all factor into the design and selection of fasteners. Another aspect a lot of people on the engineering side don't often think about is the maintenance and operation side of it as well, which is how easy is it for an operator to install and remove that fastener? Should it be installed and removed? And maybe a bolted joint isn't even the right option. But if it is something that has to get removed, how can it easily be installed or taken out and replaced? What tools is necessary? How do you assemble it such that the precision and tolerances meet the need for the particular conditions that you're applying them in? So all the aerospace fasteners that we work with are typically, well, they're almost exclusively documented in industry specifications. It's pretty rare that you're going to see fasteners which are not, and if they are, they're probably custom designed and go through a lot of the stringent analysis and test work to make sure that they meet their needs. So it's a good idea if you're early in your career to get familiar with the industry specifications for aerospace fasteners. We'll talk about some of the actual specs a little bit later. But understanding how to read those, understanding the common materials where certain things, certain features are applied, where certain materials are necessary, and understanding all the different options you have when it comes to selecting a fastener and designing a joint are important. One aspect of the story I told earlier about not using aerospace grade fasteners, well, if I go buy something at a hardware store, I don't know exactly where that material came from. In many cases, because hardware stores want to sell things cheap, they may have been manufactured in China. And that's not to say that everything made in China is bad, but it doesn't have the pedigree, it doesn't have the traceability back to who made it, did they make it to the specification, did they test it to make sure that the lot that they produced actually met those specifications, and do they keep up with, if they find something down the line where there's a defect, like a recall basically, that they can go trace that back to who used those fasteners and make sure that we replace them and repair the aircraft or spacecraft that are affected. And so in the aerospace industry, there's this long line of traceability from the raw materials to the guys fabricating the fasteners to the folks that are installing them on the aircraft and maintaining them. And if there's any defect found anywhere along that chain, we need to be able to go out into the field potentially and manage that. So, paperwork wise, that's important. Also, like I said, aerospace, we operate at very thin margins. Weight is extremely important on aircraft. It's at a premium. So, and even more so on spacecraft. So most of the fasteners, most of the materials we work with are designed with very thin margins, right? We do analysis to make sure that we have appropriate margins such that when the structure sees the worst case load, that there's still a little bit of extra strength there. But we can't do a 4 or 5x like you might be able to do in a civil engineering operation, just because the weight cannot be afforded. So because those margins are much tighter, we have to be much more confident in what the load capability of that fastener will be. So when I say that the confidence in that, what we're trying to make sure is that the material is repeatable, so that when it's manufactured, it always comes out with the same material properties within some acceptable tolerance there. And so that as an engineer, that when you call out this specification for this material, that it will provide the strength that that specification implies. Then the manufacturer of the bolt has to go verify that they have produced the bolt and using the material to that standard, and they have tested it to make sure that the group of bolts, they may make thousands of these things, but they have to go test a sample of them to ensure that there wasn't something wrong in that manufacturing process, right? Occasionally something happens, bad material gets mixed in, a machine breaks down, something contaminates the batch, and you need to catch that. And so there are processes put in place to ensure that each one of those lots are inspected. And then finally, there may be applications where any minor defect could cause a catastrophic failure. If you have a critical bolt holding on, for example, the wing of an airplane, and that one bolt fails, the wing falls off, well, you better be even more sure than you normally are that that bolt is in good condition. And so under certain circumstances, a minor defect in that bolt may, be catastrophic. So rather than just relying on the lot, we may have to physically inspect that exact bolt every time I install it on an aircraft. And so you may have to do more detailed inspections on more critical fasteners. And so there's typically this kind of layered level of inspection and verification to make sure that the fasteners we use, beyond just the design side of it, but into the manufacturing and operation side of it, satisfy our needs. And so this is why I can't just go down to Home Depot to go buy a fastener. It may be strong enough, but it may not. And so, and I have no way of knowing that for certain. And so we have to operate with specialty fasteners that go through extra paperwork, extra verification, traceability. And this is why, the same bolt that you could buy for $1 at Home Depot may cost $20 or $30 for an aerospace fastener. So it's not just because, the government is inefficient. A lot of times it's because there are a lot of extra steps that are put in place to ensure that those fasteners meet those more stringent standards that aren't necessary when you're building a deck and can put a bolt that's 5 times bigger than it needs to be in there. So let's talk about how bolted joints are designed and what kinds of things you have to consider, and materials and the types of options you have for different fastener designs, and kind of get you going. Hopefully this is just a initial kickoff on how to design bolted joints. It's a whole art in and of itself. And I've seen books that are way thicker than you would think they need to be on bolted joint design, and there's a whole study that could be done on that. But today we're just going to go into a kind of a quick study of the basics. So let's get jumping right into it. Okay, so when we're designing a bolted joint, typically you're securing 2 different materials together, and often you may have a hole that is joining these 2. We're going to just use 2 different colors here to kind of represent the substrate materials that you would be securing. And you would have some sort of through hole here in the middle that is going to accept the bolt. And then we'll use black for the bolt here. So you have some sort of bolt like this, comes through to the other side, and you'll probably have a nut of some sort on the flip side. You may have a washer or something like that underneath these as well. And then, of course, you have a kind of a threaded portion of both the nut and the bolt. And these joints are often designed, and whether it be for tension right? I'm just going to use red. Oops, tension. Or they might be used to secure shear. So for example, this plate is going this way and the other plate is going the opposite direction. And so you're going to have this side here pushing on the bolt on that, and then the other component pushing on the other side, and creates this kind of shear force through the bolt. So you may see each of these cases. Actually, a lot of instances in the aerospace world we're using shear. A lot of times you'll see in the civilian world that tension is more common, but you'll see both of these in applications. It just depends. So you'll have to be familiar with the loads that are imparted into the fastener under each of these cases to properly select it. But we'll get into the details of that here in a few minutes. So before we go too much further, let's talk about the details of the design of one of these bolts, and so we can understand the features that we have to be aware of. So here I've drawn a bolt and a nut, and we can talk about the geometry and aspects of each of these that impact the bolted joint design. So some basic terminology. Let's start here. This, of course, is the head of the bolt. And a lot of times this is where you would see the drive. That drive being the feature that is designed to allow you to tighten, torque the bolt. So that might be a hex. It might be, Phillips head recess up inside the head here. It may be a socket. It may be, many different features that you can find. And we'll talk about the details of those later. The next aspect to this is the shank. And so this is basically the unthreaded portion of the bolt. And of course it's the outside major diameter of the bolt as well. So it'll be the diameter. And then you have the threads. Some fasteners may have the threads going all the way up, but many of the, especially aerospace fasteners, only are partially threaded. And we'll talk about the details of what specifications you'll find for different types of threads. And then, of course, you have the nut, which is pretty straightforward. It has the threaded features on the inside as well, and usually some sort of drive on the outside, right? So this is often in the nut is an internal thread, whereas bolts typically have an external thread. That's, of course, the threads being on the outside of the part versus on the inside. So, and these actually do have different specifications that you'll have to consider. Now, if we look at some of the dimensions that are involved, the most simple, of course, is the diameter. The bigger the diameter, generally the stronger the bolt. And so that diameter dimension will be the primary driver on how strong your bolt is. Then you also have the length, right? And this length is always listed to the bottom of the head, to the end of the threads. So that length will be basically determining how much material that you can secure together. And it does have some aspects to strength and stiffness, because obviously longer bolts can stretch more than shorter ones. And so we'll talk about some of the details of how one goes about selecting the appropriate bolt length. Typically, when it comes to nuts, these are going to be sized specifically to match the threads of the bolt. And there are standard sizes. Occasionally you may see different thicknesses. So you may have a thickness on the nut. But most of the nuts are going to come in a standard size, and so there isn't a whole lot of variability you have to typically worry about there. We'll talk about washers in another time, but these are the major load-bearing components, and then washers can be added depending on if you need extra friction reduction, load dissipation, those kinds of things. But these are the components we'll be talking about today. So let's talk about some of the typical standard dimensions that you might find on a aerospace grade fastener. So the majority of fasteners today are still actually English units or imperial, so that would be inches. There are mil spec and other specs out there that are in metric, and you may find those, the industry may shift that way over time, but still a large majority of the fasteners we use in aerospace are English units. And so when it comes to things like the diameter, everything's going to be listed that way. Now, if you've seen even hardware fasteners, especially in the US, of course, they are still all pretty much English most of the time. You can get metric depending on your application, but if you live in the US, it's pretty standardized screw dimensions. And so the most important first dimension that you're going to be aware of course, is the diameter, right? And so that use that symbol there typically for diameter. You may see it just listed as abbreviated diameter. But the diameter of the bolt is going to be one of several different sizes, and we'll just kind of start with the smallest sizes and standardized formats in English, of course, are things like number 2, number 4, and these are just simplifications of standard screw sizes. Once we get up to number 10 in the aerospace world, we start transitioning to full dimensions. They'll use fractional, so 1/4 inch. You may have things like 5/16 and various other sizes out there. I'm just going to start with 1/4 inch today. Up to this size is about the most common you're going to see in installations of avionics, small equipment, etc. The bigger sizes start coming into more structural applications where you're using things to hold on, think like wings, landing gear, major components and that sort of stuff. And so they're going to follow the same standards that you're going to see in the smaller sizes, but they're just obviously going to be larger dimensions. So the most common ones you're going to be using when it comes to most small installations are going to be these sizes. And number 2, of course, is extremely small, and you hardly ever see those used at the aircraft level. They might be used internal to avionics and that sort of thing. But these are all, you may just see these numbers, but these all translate to specific inch dimensions. And so in this case, I'll write these out in decimal format. So number 2 standard dimension is 0.86 inches. Right, and then number 4 you'll see listed as 0.112 inches. You may see an extra decimal place here as well in some cases. So number 6, 0.138. Number 8 is going to be a 0.164. Number 10 is a 190. A lot of times you'll see or hear folks talk about dimensions in thousandths of an inch. Of course, this is the thousandths place at the 0 here. The 9 is the 10th or hundredths, and then the 1 is the tenth. So if you hear someone say 190, they're talking 190 thousandths of an inch in diameter. And of course, a 1/4 inch comes out to 25. So if you're using screws and bolts in this kind of range, these will all become very familiar to you as time goes on. You can kind of almost memorize them as you use them consistently. Now, each one of these sizes also has an associated thread set that can be used with them. Now, of course, you can make threads that are smaller or bigger, but typically bolts are going to come with a thread at the same size, standard size. So if you hear number 10 thread, you're going to have a 190 diameter bolt, and that there are rare exceptions, but for the most part that's really what you're going to be seeing. And so there are different thread types that we have to worry about. So let's talk about the threads. So this is one of the most important parts of your bolt design, of course, is selecting a good thread. Obviously you don't have to design the threads, these are standardized for a reason. But there are important different standards you need to be aware of when it comes to selecting an aerospace fastener. So if you go down to the hardware store, the vast majority of screws are going to use a UN standard thread on them. So that has to do with the shape and dimensions of the threads. And there are different sizes. There's a UNC or coarse. So this is your coarse. and then you have UNF, or you're fine. And so, of course, there's going to be more threads per inch in the fine thread than there are in the coarse. So depending on, what your application is, coarse threads are quicker and easier to put on, but finer threads, tend to have a better grip and share the load better. So a lot of times you'll find in aerospace we tend to lean towards the fine threads, but most mil-spec and aerospace fasteners don't actually use the standard UN thread form. They have a special form which is called UNJ. So that also has a coarse and fine, so it's the same basic thread, but the difference is that they have added radii in both the root and the tip. So when you look at the threads of a UNF, they can basically just do this, right? They typically have this kind of sharp thread. They may even be sharp out on the tip. And then, you have a mating thread which has to interface with that. Now, when it comes to the aerospace fasteners, the UNJs, they actually have a required radius in the thread. I mean, the tips can still be squared off here, but what you'll see is these root radii have to be such that they can clear the rounded ends of both of these internal and external threads. And so that helps with fatigue resistance. It reduces the stresses and concentrations in the corners of those threads. And so aerospace being very sensitive to fatigue, they typically use the UNJ threads instead of the standard. You may also see a UNR, and those have, I believe, one of the radii, but not both. That may be more common on socket head cap screws and that sort of thing. But for the most part, most aerospace and defense fasteners are going to use the UNJ thread. So let's talk through some of the different types of thread that you're going to see in the aerospace side. And, there are different specs we'll talk about, but mil standard, AN being Army, Navy, NAS, National Aerospace specs. So there are various sizes that are typically used, but majority of the time you're going to see 56 threads per inch for the number 2, 40 for a number 4, so that'll be a 440, 256. Number 6 is going to typically use 32 threads per inch. 8 is going to use 32 threads per inch, and 10 even typically uses 32 threads per inch. And followed by quarter, you'll see it typically listed something like this. Quarter 28 is most often used. So there are, of course, coarse versions of some of these threads that could allow you to have fewer threads per inch and make it faster to put them on. But in the aerospace world, again, we typically, when we start getting bigger, use the finer thread. And so that these are the sizes you're most commonly going to actually see. Now, one thing to keep in mind, of course, is that when you look here, these three all have 32 threads per inch, and this is very small, so that's actually kind of getting a fairly large number of threads for this size screw, and actually number 6s tend to be a little bit on the weaker side compared to most of the other fasteners for their size. So it's not something you typically use anyway below this size to make a structural application. It tends to be things that you're just holding on small components and that kind of stuff. If you start talking really needing something to hold under significant loads, we start talking about number 8 fastener, number 8 screws, bolts, etc., and bigger. All right, so let's talk for a few minutes about the strength of the fastener. Now, obviously, the main purpose of a bolt is really kind of just to use this shank section of the fastener to take the tension or the shear loads in the joint. And so when you have bigger diameters, you obviously have stronger bolts. And that can be just simply observed by looking at the cross-sectional area of a bolt. So if I were to cut a cross-section, you would have some diameter, right? And so, of course, you can calculate that the area of that. Pi times the radius squared. So the area of that will become the value you use depending on the material and to get the total strength of the fastener. So you're going to have a certain amount of strength in shear and tension, and that's going to be dependent on the cross-sectional area of this diameter, as well as the material properties of the material the bolt is made out of. So if it's steel versus aluminum versus titanium, they're all going to have different strengths, obviously. So even for the same diameter fastener. Now, another thing that a lot of folks don't think about when they're first getting into the industry and designing bolted joints is a lot of times you're going to have both shear and tension applications, right? You're going to have a possible situation where the bolt is being sheared and it could also have a load that is being imparted on it. And so that may be, for example, I've got a box and it's going to take a load one way, and then that causes the bolt to, the box to torque, and that creates some tension as well. And so if you were looking at a chart of strength on the bolt, you're going to have, let's say this is tension and this is shear. You're going to have a certain strength for each of these, and how much material or how many pounds per square inch or how much force you can take depending on the size. That's going to be tension and a shear allowable. Now, if you're combining those, I can't just go necessarily to the limits of both at the same time, right? So if I'm pulling the bolt at the absolute limit of its tension, it can't take any more shear because that's going to further load the material. So in reality, there's typically some sort of curve in here that you should account for. This is typically an elliptical curve for estimates, but that basically means if I have, say, half the shear strength or half the tensile load, then I might be able to take some limited, there's going to be less than the maximum amount of shear I can put into that bolt. So when you're designing it, you're going to have to consider whether or not the bolt is being loaded in different directions at the same time. But that's all based, of course, again, on the available cross-sectional area and the material properties. So let's take a quick look at how you calculate that. So let's go through a quick example and assume that we're going to use a number 8 screw, and so we can calculate the cross-sectional area of that for this equation. In this case, we're going to use 0.164 inch diameter, and of course it has to get divided by 2 to get the radius, squared times pi, and I've calculated that out to come out to 0.0211. That's going to be inches squared. All right, so let's assume I have a material strength of 100,000 psi. You'll see it psi or KSI for short. So a lot of times it's listed as KSI if you're using English units. You may see it in megapascals, but a lot of times, again, if we're operating in the aerospace world, sometimes it's a lot of English fasteners or English units. But all this could be done exactly the same in metric. And so if I have 100,000 psi capability, I multiply it by the area. So of course that's 100 ksi times 0.0211 inches squared. So that inches, of course, cross out, and then you're just left with basically, let's call it 2,100 pounds that you can take with that one fastener. So a number 8 fastener with 100 ksi material should be able to handle around 2,100 pounds worth of tension load. So you can now use that to understand what kind of strength that you have in your joint. Now there are other factors we'll have to consider, like the base materials, whether or not they can themselves transfer that load into the bolt. This is just the capacity of the bolt itself. The nut may have a weaker strength. Typically you try to design a nut select a nut that can actually handle as much or more than the bolt. And so the standards out there are designed that way. So typically you're looking at the fastener strength. And there are tables for all of this, of course, that have been all pre-calculated for standardized materials so that you don't have to necessarily go through manually calculating this for every individual fastener out there. But understanding the basics of how this comes about is pretty straightforward. Helps you understand kind of what that limitations are, especially if you find yourself in a situation where you're selecting an unusual fastener, something that is not part of a standard. Same applies for, again, shear strength might be something different. It might be 50, 60 KSI instead of 100,000. And so, you just put in different numbers for those conditions. Okay, so let's spend a minute talking about the selection on the head of the bolt. Now, there are a lot of different types of fasteners out there, a lot of different head types that you can find. And some of them, certain applications, it may not really matter that much as to which type you use. In other cases, it's more you're just going to find standardized ones because the bolts have been designed to accept significant loads and in certain ways of fastening them. So the most common ones you're going to see, of course, if I look down on the top of the bolt, I'm going to look down and see something like, for example, a hex pattern. Right, so it's a typical hex bolt that might be similar to what you might find at a hardware store, but in aerospace, they're just going to be made of different materials and different standards, but generally they have the same type of hex drives. You of course could find a typical Phillips head or flathead kind of screw. These are the different types of drives that you might find. These are still pretty common. They're very frequently used because they're easy for tooling, right? So you can just grab a standard screwdriver and operate, any of these types of screws. And so, it makes it really easy from a maintenance perspective. However, if anyone's ever tried to work with, these types of drives, that Phillips head screws strip out really easily. Flatheads can be hard to keep the screwdriver in place. And so there can be certain applications where that just doesn't make sense. Since we're kind of talking about the drives, there are, of course, other things where you may have like an internal hex, a socket head, or Allen key, depending on how you want to refer to it, where the drive is inside the head with a hex. There are other standards too. In the aerospace, a lot of times you'll see what they call an offset cruciform. So it has kind of this pattern to it. And so it's very similar to a Phillips, but it's offset, and that reduces the cam out action. And so you can actually get better torque on those. They can be a little more tricky to get out, but they're really good for applying additional torque in. There are other things like Torx where they have, kind of like an internal star pattern. I'm not going to draw it out to super precise. And there are others as well, but these are kind of the more common ones that you're going to see in the aviation and space world. When you look at the cross section of the head as well, we've kind of drawn here is basically like a hex bolt head on the left, and so that tends to be fairly flat. It may have a little bit of a depression, a dimple on the inside, kind of up where you would typically put a driver. In this case, with the hex, you're driving it from the outside, not an internal pocket, and so there's some material taken out there. If you're looking at any of these types of standard drives, like a Phillips head or something like that, the most common ones that we see are what would be referred to as a pan head. It's kind of round like this, and has this kind of domed shape to it. There are subtle differences between that and a few other types, but what we'd refer to as a pan head is the most common. And so then, of course, the Phillips drive or something like that is built into the head. Another type that you might see is a flathead, of course, and this is designed to go into a countersink, right? And of course you have your drive here, and that allows you to put this fastener flush to the surface. In fact, what I should probably do is draw these such that I have a surface here that they're going to be mounted to, and so the bolts going down through here. But in a flathead, you're designing it such that the fastener sits below the surface, and so that you can have a smooth surface, either for aerodynamics or for making sure you don't snag your clothes or hands on things, or clearance for another component sitting over top of it. So there are a variety of reasons you might use a flathead. Now there are a few others out there you can find. It's actually, instead of, from a cross-section wise, it looks like this, but it's actually round. When you look from above, is called a philister, which you might get used in a certain applications. Just depends on whether or not it's something available, something that you're driving for that type. Similarly, for like a socket head, socket heads tend to be used more where you're again, this is like an Allen key. Something has a much thicker head so that the Allen key can get up in there. They tend to be a little bit narrower, so they're good for going down in pockets where you might not have as much access. Let's see, occasionally you may see a washer head, so it's very similar to the pan head, and it has this shape, but it has kind of a built-in washer on top of it, and so that tends to make it a little bit wider and cover more area if you have a larger gap. Occasionally you may see something that is like a hex on the outside with a actual cruciform of some sort, like a Phillips on the inside. And so that can be kind of like a combination head, and that has some advantage in that you can drive it with a standard Phillips head screwdriver, but if you strip that out, now you still have a way to get the fastener out with a socket of some sort. And so if you have some cross compatibility there. So majority of the time I've used pan heads for standard applications where you just need a screw to go in and hold a box down or something like that. Again, flat heads are going to be a little bit more common for where you really need to have the head sit below the surface. Those are going to be weaker than some of these other types because of that. They're cutting into the material that you're using to secure it. Again, heads might be used where you're going to have a little more flexibility in the hole size, and you want to cover that a little better. The sockets, of course, like I said, will probably be more where you're trying to get down into a pocket where you have a tight space or somewhere where you can't afford a larger head. The hex heads tend to be used more on structural bolts where you need to get a lot of torque on them, and so similar to the hex heads, you may find a lot of we'll go back to the top-down view of what would be called like an external 12-point star or triple square kind of thing, so that if I draw multiple squares, you can see I start to get this star pattern, and that kind of looks terrible in this view because it's kind of small, but you kind of get this star pattern in the fastener, and that from a cross section wise actually looks like this. And you see this a lot on high strength bolts, high tension bolts in the aerospace world, and it has this kind of star pattern when you look down on it. There may be spline drive is very similar. Usually it's like a 12-point, it's like a multiple socket kind of setup, so that it allows you to get a lot of contact points in the ratchet or the socket that's tightening the bolt. And you can see obviously with the taller head, it has a lot of strength capability in that. These are kind of the most common ones you're going to see. There are probably a few others out there that pop up on occasion, but these are the majority of the ones that you'll have to contend with. Now we can talk briefly about the nuts, of course. There are a lot of different options when it comes to how you tighten the bolt. The nut is providing, with the threads, it's driving and pulling tension on the bolt to try and tighten it up against the materials. And so a lot of times you want that to have a very tight grip onto the bolt. And so in the aerospace, we typically try to have at least two methods, two ways of securing the bolt to make sure that that thread doesn't come undone under vibration. And so a lot of the nuts that you'll see here have a locking feature built into them. Now that may be some sort of plastic insert that is in the nut. So if you've ever used a nylock nut, that may have like a little insert that is kind of added into the head of the nut there, and that provides additional friction and grip onto the fastener. It is used, certainly if you're on an airliner and you look down at the seat that you're sitting on and the person in front of you, maybe under their seat, you can probably see a nylock. I've seen that a lot on the seat mounts. There are limitations onto the environment and temperature you can use those and how many times you can cycle them. So they're not as common, but they do get used. The most common type is a distorted thread. And so instead of having this nice circular thread pattern on your nut, a distorted thread actually has a little bit of a kind of an oblong shape to it or something like that, so that when you are tightening, the bolt will actually push the nut back out, and that creates a lot of compression and tension in the threads. There are other features which you may find, even locking features that are added, like a plastic piece or something that's actually inserted into the bolt side. Or you may have a situation where you have like a through hole that goes right through the bolt here, or through the nut, and that can use like there could be a hole in the bolt here, and that'll be a cotter pin that you can throw through that, and so that's another piece of metal that prevents the two from untorquing relative to each other. And so you have this cotter key that goes through once the bolt's in place, and it goes through the bolt and the nut and prevents the two of them from separating. And so if you've ever seen what they call a castellated nut, so if I look kind of in 3 dimensions, most nuts might look something like this, with kind of a round base to it. The castellated nuts have these little pockets that are kind of cut into them. You'll see them kind of look like this. There's still an opening in the middle here, but these little castles are little openings that allow you to put that cotter key through there once the bolt has been tightened up. And so you do see that a lot in the aerospace world. Another thing that you may see is nuts with holes drilled in them through the corners. So let me draw it again. It's probably easier to see in more like a 3-dimensional space. But if you have a hex nut that looks something like this, there might be holes drilled through the corners of these edges here, and that allows you to run safety wire through that. So once you've tightened this up, you can run some wires through here, you twist them together, and then it can tie on to another nut here, and it's designed in such a way that if one of them tries to loosen, it tightens the other one, so they fight each other the whole time. And so that's another locking feature that may get used, especially in high vibration environments, to prevent any nuts from coming loose. And so now it's not just a friction lock between these, it's a mechanical lock that the material in that wire is preventing the nut from coming out. Okay, so I wanted to go into the actual details of the joint itself and how that is selected and designed. So typically, of course, you're going to have 2 materials. We're just going to call them material A and material B, of course. These are most often in the aerospace world, they may be aluminum, they may be carbon fiber or other materials like that. Ideally, these are the same kind of material because you have to be careful about certain things like dissimilar metals and that sort of thing, but that's a whole other aspect of joint design that you'll have to consider down the road. But today we'll try and focus on the bolted portion of the joint design and how one goes about sizing all this. So what I've drawn here, of course, is the bolt in black. I've drawn washers in blue, and so there's one on the top and one on the bottom of the joint here, and then the nut in the purple here. So, this is your nut, and this is just the head of the bolt up top. I've drawn in these sections for the washers. So when you're designing this, you have to consider obviously the thickness of the two plates combined. So if I'm joining these two materials, I can simply, of course, add the thickness of one to the thickness of the other and get the total thickness. Right, so that'll factor into how long of a bolt you're going to need. Now, of course, often washers are used, and you'll have to consider the thickness of the washer, and that's 2 of them, right? So you have 2 times the thickness of the washer plus the thickness of A plus the thickness of B, and then you actually have the height of the nut. So I'm just going to add it on to the front here, height of the nut, and all of that should give you your total thickness. Now, what we're talking about here is just up to this point, and so that would take from the bottom of the bolt head, right? So the top of the washer all the way to the other end of the nut. And so this is going to be our current total thickness. But I also have this protrusion drawn here on the bolt. Now, typically in the aerospace, we'd like this to be 2 to 3 threads. It can be a little bit more, but of course, the longer that is, the more weight you're carrying that you don't need. And in aerospace, weight is very important. So typically, you design to be in this kind of range. If it's less than 2 threads, these last couple threads on here, as I showed before, might be a little bit tapered. They may not be full threads. And so that's why we want to make sure that there's at least 2 full threads sticking through the other end of the nut. This also provides a little bit of flexibility in case the nut starts to come loose. It doesn't immediately fall off. So, but the most important reason is to make sure all the threads are fully engaged with the nut. So that will be, you need to make sure you plus those 2 threads for your total thickness, and that'll give you the length of your bolt. So when you're selecting the size of bolt that you're going to use, that's how you'll calculate how long of a bolt you want to use. Now, you may also want to consider the tolerances in each of these dimensions, right? So the thickness of that plate that you're mounting, plate A or B, may have 10, 20 thousandths worth of variability. And so you may want to check what's the worst case, worst on worst of longer dimensions. What are the shortest dimensions things could be? If that changes, between sizes, that maybe, the lengths only come in certain lengths. Sometimes they go up by 1/8 of an inch, maybe 1/16. Depends on the particular fastener type and size that you're talking about. And so you have to consider what are the tolerance impacts to that. Maybe I have to be able to use 2 different sizes depending on how the individual components come together. Or maybe I got to increase tighten the tolerances on the parts I'm manufacturing so that I have a consistent joint here. Maybe I don't want the thickness to vary by 50 thousandths on part A because now I don't know what size bolt I'm going to need day to day. And so those are considerations that you'll have to take into account when selecting the bolt size. A lot of times if you're designing something in a hurry, you may want to consider just buying different sizes in case you got the dimension wrong. I've seen a lot of programs where we're in a real hurry and the engineer says, this is the length bolt I need. It needs to be 1.25 inches. And then, we go to build it and we're off by 1 size. We need to go get a smaller one or a longer one. So that's how you go about selecting the length of your bolt. So now we talked about how to calculate the total length of your bolt. There's another aspect to this that we need to consider, which is this section in here, the unthreaded portion of your bolt. So again, this is kind of your shank inside the fastener. If you've gone to a hardware store, most of the time you may see bolts and screws that have a full thread. The whole length of the screw is threaded. Now, that makes it really convenient in the sense that I don't have to worry about, how much thread do I have? Do I have enough to cover the nut? Do I have enough to make it through the material without, bottoming out the nut on a unthreaded portion? But the disadvantage is that if you have a fully threaded, fastener that's going down this entire length, that these loads, especially when they're in shear, right? I'm running shear loads side to side, whether it be this way or that way. That can force load into a sharp point within the fastener. It's not as strong in that section, and so now instead of the full diameter of the bolt, you're working off the minor diameter of the threads, so the shear strength is actually reduced. And so nominally, if you're using a shear joint, you don't want to use threads to bear that load. So what you want is a unthreaded portion here. And so rewrite the A and the B here. But you want this section in the middle to be unthreaded so that when these two plates are pushing against the fastener, they're in the thicker section of the bolt. Now, typically this is just the same dimension as the thread. The outer dimension of the thread are pretty close to it, maybe slightly larger. And we also have to consider the dimensional tolerances to get the bolt in. But you need to consider how long it is, and the spec for your individual fastener should tell you, how much length is taken up by the thread and how much is taken up by the shank. Typically, they're probably going to give you this dimension on the thread and not the shank dimension. And you got to make sure, again, when you're selecting the length of the bolt, that thread doesn't stick out so far that the unthreaded portion starts running into your nut, because then you won't be able to actually tighten the bolt all the way. But ideally, you want your unthreaded portion to actually protrude all the way through the material. So it's this fine balancing act of trying to make sure there's enough thread that I can tighten the bolt properly, but not so much that I'm loading up the joint on the threaded portion of the bolt. And so this is where the nuance typically comes in the aerospace side of things, is we have to be very precise about these things. Okay, so when you're drilling holes through material or putting holes in there so that you can drop a bolt, I mean, it seems pretty straightforward. It's just a straight hole, but now we have to start really worrying about the tolerances that we're dealing with. So it depends on the type of joint, right? So if we're pulling this joint in tension, where we're pushing up on the bolt here and down here, really what we're talking about is these materials are trying to pull apart. And, whether or not there's a gap in between the bolt and the base material, as long as it's fairly small, it's probably not going to make much of a difference. Most of the load's going to be coming through the middle of this washer and nut interface, or the base of the head. And so the fact that, there's clearance there isn't really a big deal. And so a lot of times if you're running a tension joint, you can kind of allow a little looser fit, and that makes it easier to install, and that allows for the plates to be a little bit offset. And so, it makes a much simpler design from an installation standpoint. However, which is commonly the case in the aerospace world, these are actually in shear, where these plates are going in opposite directions. Now, if there's a lot of space there, the bolt has room to move, the joint can slip and shift, and so that can make asymmetric loads on the bolt. And so when you're dealing with shear, you typically want that to be a very tight fit. In fact, this is why in the aerospace side of things, we typically rivet aluminum together, right? Is that when you buck those rivets and squeeze them together, they fill the hole completely. There's zero space left. And so when you talk about shear joints with bolts, this is where tighter tolerances start to come into play. And so now we start talking about the diameter of the bolt versus the diameter of the hole. If you make that too tight, now it can be really hard to get the two parts together, right? Because let's say this part wants to be shifted, part B wants to be shifted a little bit to the right. If there's only like 2/1000 of clearance, 2/1000 of an inch clearance between the bolt and the material, that plate can only be off by 2 thousandths, or the location of that hole can only be off by those couple thousandths. So, you have to consider when and, is it need to be super tight and when does it not to be. This also comes into play on how you fabricate. So it may be that maybe you design A and B such that they come in with a extra material, and there's maybe only a small pilot hole, we call it, right? So it's not the final hole size, right? That's a smaller diameter hole, and then we get a little pin here, we locate where those holes are so they line up where they're supposed to be, and then we drill the one next to it, and when you drill it, you match drill, right? So you're drilling through both materials at the same time, so at least the location is no longer part of the tolerance, because the two holes were drilled at the exact same time in the place you want them to be. And so that's one way to mitigate the effect of having a really tight tolerance but needing the flexibility to locate a plate more generally. So you can locate it first and then drill it by having these two parts drilled independently. All right, so let's talk about a few variations on the bolted joint design. So in many cases, you may not actually be using the traditional bolt with a nut on the far side. There are different options you can have to secure the bolt down that don't involve just a standard nut. So what I'm going to do now is let's erase this, and what we're going to talk about is first is an option for what we call a nut plate. So this is actually still a nut, but in this case, instead of a washer and a free nut that are just basically stuck on the back end of the connection, we actually have a permanently attached nut plate. So it'll be something like this. You'll have a nut in this assembly, and I'll show you what this looks like in a minute, but that is mounted to a plate. So this already kind of looks a lot like the washer nut combination, but what happens is the nut portion of this assembly is actually captured by some sort of mechanical assembly such that the nut is always retained in there, and it may float within there, or it may be a permanent fixed part of the nut plate. But the idea is that you have something that can't fall free when you take the fastener out. So when I remove the screw or bolt, the actual nut is still retained on the structure. In this case, material B here is the basic structure that's holding it. And a lot of times these can be glued into place, like bonded in, but more often than not with aluminum structures, they're going to be riveted. So you may often see there'll be some flesh head rivets that are stuck in here. They go through a hole in the bottom of the plate on either side, and those are riveted, like bucked into place with a bucking bar, or they may be like a pull rivet or something like that. But these rivets then basically permanently attach the nut plate in purple here to the base material, in this case is green. And that means that you have a retained a threaded fastener, and so that helps particularly in the aviation and even in the space world. If you have a connection and someone needs to go do maintenance, they need to remove a fastener or something like that, this reduces the amount of parts that may come free and potentially create a FOD, foreign object debris or damage into the vehicle. And so it just makes maintenance life that much easier, assembly life that much easier, because there are just fewer pieces that could fall out and potentially cause headache down the line. Now the nut plate's going to be slightly heavier, and so if you've got thousands of these things, that can add up. If you've got mounting an avionics box or something like that, a lot of times you will use a nut plate configuration like this, because you're frequently taking avionics components in and out to replace them or do maintenance, and having not having to reach to the backside to undo those nuts all the time and potentially drop them in a place you can't get to them saves a lot of effort. So you'll see nut plates used a lot in the aerospace world, particularly if there's areas where you have to limited access as well, right, where you can't easily get to the backside and put a wrench or something on the nut that would normally be on this backside of the interface. So another possibility is the what we'd basically do a threaded insert, and this is more commonly going to occur if you have a thicker material somewhere where you don't want a very long bolt to go all the way through, or there may be some like a pressure application where you don't want to go to the other side. And so perhaps this base material in green here is actually really thick. You know, maybe it's a much thicker piece of material here, and you don't want to run a bolt all the way through. And so this is where you would potentially have some sort of threaded interface in here. This may be just a simple tap, where you just tap the thread shape into the component, or you may tap and then put some sort of insert. You may hear of helicoils, helical inserts, or other types of inserts that you can put in. Those are separate components that may get put into something that might be, for example, a hole that is drilled down into the part, and then an insert that is added later that fills up this part and provides the threaded feature in there. And so that's another application. You know, that a lot of times you don't want to use just tapped aluminum just because it's very soft. It doesn't hold up very well under repeated use, and so we often use some other material. So for example, maybe this threaded insert that comes in here is actually a stainless steel or something like that. You'll have to make sure the materials are compatible because you'll have dissimilar metals in that case, but a lot of times you'll use some sort of insert like that into the material there. I can talk briefly about the heads of bolts. Let me pause this. So let's take a minute to talk about the heads and how those interact around the top of the joint here. So there are actually a couple of regions of interest that you'll have to consider. Obviously, with you know, a standard bolt and that sort of thing, we're going to have some sort of washer typically underneath it, and that is partly to provide more bearing surface, and that is where we take the load. So I'm just going to redraw this over here in a little bit bigger detail. So you have the bolt here coming through, and if you're looking at the material underneath, I'll draw orange again to kind of match the other view. You know, you have this hole opening, and so you're trying to transfer load up into the bolt. The washer provides a little bit more room for this surface area to start transferring that load. And so especially if you have, for example, a softer material like the aluminum here as the base material, and maybe the washers are steel, those are going to perhaps deform less than the aluminum will. And so if you spread the load over a wider area, the steel can take it, you know, in these thin washers and in the bolt, but the aluminum may need more surface area to distribute that load more evenly and reduce stress concentrations. So that's one function of the washer. The other is that when you're torquing the fastener down, this provides a bearing surface on which you can have two hard materials like the steel of the bolt and the steel of the washer that can rub against each other, and so you're not galling and wearing into the aluminum underneath, or carbon fiber if you're using a composite material or something like that. So there's kind of a couple functions that the washer can provide. It also, you know, can help cover up some of the gaps if you have a large opening or something like that, although, you know, generally we try to, you know, keep a fairly tight tolerance on the bolts in the aerospace side if we can. And so, you know, unless you're doing a very large, you know, interface that is designed to potentially adapt to a lot of movement, you're probably going to be using just a standard small washer simply for that extra bearing load capability. When you look at even closer and kind of the zoom in here on, you know, what is the corner here of where the head and the bolt come together, a lot of times you'll see, you know, a screw may have a radius. You may even have like a little bit of a boss extrusion coming out before you hit the actual main part of the shank. So if this is kind of the head up here, this radius that is in the corner here, again, this is very similar to what we talked about with the threads. That is to help improve the fatigue resistance, because if you have a sharp corner, you're going to get a lot of stress concentrations in that area. And so having a radius, you do radii a lot in the aerospace design world to help minimize those stresses. That can improve the fatigue life of the fastener, and so we do that quite often. Now, what you do have to consider, of course, is that because that radius is there, you don't necessarily want a washer that has a sharp edge right up against that, because as soon as the head comes down, it's actually going to eat up, and put some load into that joint. And so really what you want to do is, I clear this out and kind of redraw it for you. If you have a radius like this, you either need a washer which has a wider radius in the opening, right? So if the center axis of the bolt is on the left here, this radius, the diameter of the opening, needs to be large enough to avoid contacting the radius of the head here. Or another option is there are particular washers. These tend to be more used in very high strength tensile applications, but there are washers which have a chamfer corner cut out of them like this, and so they might be more like this green shape here, where they've actually intentionally designed in that chamfer to allow a tighter fit up against the radius at the bottom of the head. Now, another aspect is if you're using a flathead bolt like this one over here, the material that you're working with has a certain thickness, right? And so depending on whether or not you're providing a tension joint or a shear joint, that the amount of material that's necessary there may be different. But you do need to consider the fact that when you do a flathead like this, you are cutting into the base material to put that fastener in there, and that weakens the material, particularly in you've got shear loads, and you get a little bit of surface up here that you can shear into, but a lot of this is reduced. The other thing is, if you're pulling a tension load right on this, you're trying to rely on this contact area to transfer that load, and so if you've cut down the thickness, now you don't have the full thickness that you had to start with. You only have a tiny bit of it, depending on how deep that chamfer is relative to the base material. So generally speaking, we don't want to eat too much of this, and we don't want this to end up as a sharp. So what I mean by sharp is, if my fastener head looks like this and my base material is only this thin, I have a sharp corner here, and that obviously is fairly weak. Very little of the material is left there, and so it can't take much load, and so realistically you're losing the very edge of that anyway. And so if you're already cutting that short, you've taken what is a bad situation and made it worse. So depending on the particular application, that might be okay, but generally we try to avoid this, and we try to make sure that the material that we're fastening has at least some flat here, and ideally we're not exceeding maybe 2/3 of the thickness of the plate. Now it's even better if it's thicker than that, but you want to make sure that the head doesn't go too far in there. One thing we didn't talk about with flathead fasteners earlier was that these come in different angles, right? There are different, it's a cone that we're trying to work through, and so there can be different angles that are provided in here. This is basically the angle we're talking about here, and this is the cone angle. In aerospace, we typically use 100-degree angle fasteners. You can see 82-degree, and this is more like the type that you would typically find at the hardware store. And there are times that they do have mil specs for those, but the vast majority of the fasteners we use are 100-degree. So you'll do a 100-degree countersink into the base material to make sure that angle matches the angle that the fastener head does. Because if you use the wrong angle when they machine the part, then the screw's not going to sit properly. And speaking of countersinks, we have to design in that cut into the basic material and make sure that it is appropriately sized. So if you drill a hole into a plate to make room for this screw, there's typically going to be some dimensions we have to worry about. Let me make them red so it stands out here. We already kind of talked about what this angle is, so some sort of angle on that. And then there's your diameter of the countersink, and of course you have the diameter of the through hole. So if you are machining this, you're going to have some sort of countersink here. It's going to have some sort of angle and diameter to it. So the callouts for these, maybe I'll just move this to the side. This is going to have some sort of callout indicating this is a symbol for a countersink. It'll probably say countersink 100 degrees, and then you'll have some sort of diameter associated with that. And that should be such that big enough that the diameter of the head of the screw can sit subflush, meaning below the surface up here. Now, in certain instances, it may be okay if it protrudes a small amount, but usually you're using a flathead because you want clearance from the top of the material down to the bolt head. And so you have to make sure that that diameter is of the correct size to allow that to happen. And make sure you account for the tolerances. Again, for the head diameter can change a little bit on the bolt. The machining diameter of the base material can vary. So, depending on what that is, I'm just going to make something up here. Maybe that's 0.385 inches, right? So depending on what that is, you'll have some sort of tolerance associated with that to make sure. And you often have the corner here on the bolt is not perfectly sharp, right? It's going to have a small flat to it, and so you may have to kind of determine what the projected diameter of the head would be to ensure that it sits flush, because really what you're trying to do is make sure this top surface is below the material. So let's talk briefly about the materials that we might use in this kind of assembly. Now, more than often, like I said, the structures that are used in aerospace, and particularly the base materials we're talking about here, this is most often going to be aluminum. It might be carbon fiber reinforced plastics. It might be fiberglass. It might be titanium in some instances. There could be other things like Inconel and corrosion resistant steels and what have you. But it just kind of depends on the particular application. One of the considerations when you're designing a joint like this is making sure your materials are compatible with the substrate materials. So if we're dealing with aluminum, then a lot of times we're trying to find steels or finishes with the steel that are appropriate for that material. So in the aviation world, cadmium plating is often used as an outer finish on the bolt, and that is often with what we'd call an alloy steel. So the alloy steel is what makes up the primary constituents of the bolt material, and then the cadmium is just a coating on the outside. Now, cadmium has its downsides. It is a toxic heavy metal, and so you want to minimize personal exposure. And if you do handle those bolts, it's a good idea just to wash your hands after you're done before you eat something. But cadmium is used primarily because it is very compatible with aluminum. It does not provide a large voltage in the galvanic sense. So it's not going to cause a lot of corrosion. That's why it's selected as the primary coating for most aviation steel bolts. It is not used typically in the space side of things, because in the vacuum environment in space tends to grow tentacles, grow these dendrites and things that come off and can cause all kinds of other problems. So that material is typically not used in those environments. You might see nickel used in certain situations. So alloy steel as the base material is kind of the most common, the most basic fastener. It's what you would expect. It is a high strength steel alloy that allows for a lot of load capability. Steel is always going to be heavy. I mean, all the different steel variants are going to have very similar densities, so weight-wise, it's pretty typical. But the alloy steel is just kind of like your typical go-to. Now, if you need other types of materials, there are other options. So a lot of times you will see corrosion-resistant steels, or CRESS is often used as an abbreviation. This is most often the 300 series of stainless steels. So you may see like 304, 316, that 305. These are stainless steel varieties. They're very corrosion resistant. They're not as strong typically as the alloy steels, although some versions are pretty close. But they are good for compatibility in corrosive environments. They get used a lot with, for example, carbon fiber and that sort of thing. They can be used with aluminum, but that it's preferable to use some sort of other coated materials if you can. Above CRESS, because CRESS, this 300 series is somewhat limited in its strength and its heat tolerance, then you can go to another material, which is kind of a variant of a corrosion-resistant stainless steel, but it has other alloys more in it, and this is A286. So that is a material that has a higher temperature and higher strength capability. So it's more akin to an alloy steel, but it's more like a stainless in terms of its corrosion properties. Galvanically, it's less compatible with aluminum, but it can be used in those situations depending on what your allowances are and how you protect the materials. So A286 is a common material used in the space environment, as well as a lot of 300 series steels. So these are kind of your most common ones. So you're going to see some sort of alloy steel. This we'll have to look up the specs, but these are high strength alloys. So they do corrode if they're not coated properly, whereas the CRESS and A286 tend to be more resistant to just environmental corrosion. But that doesn't mean you just let them go. You have to make sure that they are still compatible with the materials you're working with and they're appropriately protected for the environment you're operating in. You can occasionally see titanium, different titaniums used. Titanium 6-4, I think that's 6Al for vanadium. That titanium, it's pretty common. It's used a lot with composite materials, carbon fibers, and that sort of thing. The downside, of course, is titanium is expensive. It's hard to get a hold of. It's hard to work. So a lot of times it's only used where it's really necessary. Another variant is Inconel. That material, there's different types and alloys of Inconel, but this is basically a nickel-based alloy, which is designed for much higher temperatures, so those may get used in environments like engines, compartments, and propulsion systems where the temperature is very, very high, and so it can hold those material properties longer. I think, we kind of talked mostly about the coatings for alloy steels. That's something you'll have to consider, mostly based on the materials you're using and what's compatible. But most of this is already defined in the specifications in terms of, this particular alloy has this finish available. You may occasionally find different options of different finishes to be allowed with a given material. And if you don't know which one is the right one to use, you should talk to a senior engineer. But a lot of times the cadmium again is good in the aluminum space, or aerospace, meaning the aviation side of things, and there may be other finishes and alloys depending on the space environment that have more strict material finish requirements. So make sure you check in on those to make sure you're selecting the appropriate material for what you're assembling. Before we go any further as well, though, I do want to mention that things like washers, these are typically just going to be similar material to the bolt. But there may be situations where you want to use something different. Occasionally we actually can use like aluminum, copper washers and that kind of thing if we need extra electrical conductivity. But again, you're going to have to make sure that you're considering the interface requirements for this interface. So aluminum is typically just used if I need to put a electrical bond to aluminum. Whereas structurally aluminum is a little bit weaker, so it's not typically used for high strength bolt assemblies. All right, so let's talk about some of the specifications that are involved with identifying your hardware that you might use in a bolted joint. So if we go really far back in the 40s, 1940s, the most common specs you see out there are these AN specs. So this was the Army, Navy, the U.S. Army and Navy agreed on a series of specifications for a lot of their hardware that they were commonly using between them. There are a lot of basic fasteners that still use that as a designation, although they've typically gone to a newer spec that actually defines the properties that have kind of superseded the old ones, although the part numbers often still reflect the old AN numbers. So if you see AN, that's what that is referring to, is just an older spec. Obviously, there's the mil spec. Most people generically have heard of the military specifications. That is very broad. The federal government, the U.S. federal government, controlled all the specifications for all the MS fasteners. So if you see a part with an MS part number in it, typically, or maybe even just an M, but usually an MS part number will be controlled by a military specification defined by the U.S. government. Now, they do have a website that lists a lot of these, both the AN and the MS specs, although I will say the vast majority of those have now transferred over to commercial control, but you occasionally can still find a lot of these. If you look up assist quick search, the government has a website that allows you to search by, for example, the MS number. And so if you have a fastener that you're trying to understand what is the proper dimensions that I should be considering for that part number, and what are the materials available, and all the tolerances and everything, all the requirements that are needed to manufacture one of those fasteners are defined typically on those specifications. And so if you go to the Quick Assist search site, a lot of times you can find some of those. A lot of them are scanned from old paper copies, and so some of them are really hard to read, although many have been updated. Unfortunately, a lot of them have been transferred to other industries, standards organizations, and so you will probably need to pay for subscriptions to get access to the more modern variants of those. But even though you may not have the current one, a lot of times you can find what you need off that Quick Assist search site. Next most common one that you're probably going to see is NAS. In fact, this may be the most common that you're going to see in the modern era, and this is the National Aerospace Standards. Now the NAS standards used to be kind of managed, still kind of at a level, are managed by AIA, which is the Aerospace Industries Association, but they've also worked with ANSI to control those specs. So you're going to find a couple different ways of getting that. Again, that's a separate organizations. They are not government. They're privately managed, and so that a lot of times you will have to pay to get access to the data for those. And there are companies out there like IHS that actually manage subscriptions to get entire databases full of that information. But if your company that you're working at has access to the NAS standards, that should be pretty common. But NAS fasteners are perhaps the most widely used today. There are other specifications, but these are the most common ones. So I'm just going to stop it there, and we can spend some other times kind of reviewing, what are the available standards and how do you read them. Before we go, I will probably take you right over to another specification so we can take a very quick peek at what that looks like. Okay, so what I've brought up here is a specification for an example of a fastener in the MS brand or MS series mil specs. Now this one is superseded by a newer NAS standard, so this is an old copy I pulled up off the government website because it's free. And so in this case you can see the spec listed up here. So this is MS 27039. F is just the revision number and the date for that revision. So all the part numbers will be referencing the MS 27039 in this case. And the specification kind of tells you the general style of fastener. In this case it's a machine screw, has a pan head, and then it's intended for structural applications, and it has a cross recess, basically a Phillips head. And so this defines the details. You'll see sometimes you have like reference to a specification here, which often provides a lot more detail at a lower level than this document does. But you can see a general outline. It's kind of hard to see in this image, but it gives you the rough dimensions. You'll see the labels here, and then there's a table further down that provides all the details for different sizes. It tells you the tolerances on things like the length. Again, it shows you here what the grip, this is kind of the shank of the fastener, the grip size. And then, the chamfer here on the end, it gives you a radius we talked about in terms of underneath the head. And so you have most of the dimensions that you would need to properly design a joint around this fastener. I'll scroll down a little bit more. There's a variety of notes. You can read through those if you get a chance. Like I said, there are different materials. In this case, they have an aluminum option. Manganese, not something you use very often. The alloy steel, that was what we talked about, is a type of alloy steel for high strength applications, and corrosion resistant steel. In this case, it's an A286 based alloy. So these are the different coatings that you can see. This doesn't mean you can use any of them with any materials above, but this is just telling you what specifications those finishes are made from and what the options are. The tensile strength, this actually outlines what the material strength is for each of these materials for you. And then you have, again, the standard threads. This Fed standard defines what the thread geometry is, which would meet one of the standards we talked about. Just a few other codes and things for reference. This tells you here how to define the part number, so depending on what size you're looking for, what materials and finishes, and what lengths, this tells you how to read those. And then you have things like tables that tell you for each size what the actual dimensions were per that diagram that we saw above. So the diameter A is the main shaft diameter, the B is the head diameter, etc. So you can figure out what dimensions those fasteners are depending on the particular size you're looking at. They actually, again, give you, based on the material properties listed above and the dimensions of the fastener, what the material properties are. Sometimes these account for some additional uncertainty and variability in the materials, but usually this should match kind of the mathematical numbers for strength of the fastener compared to the dimensions you see here.
This then gives you all the different dash numbers. So at the end of each part number, we said this is the MS27039. You'll get then a dash number that comes on to the end of the part number, and these dash numbers tell you what is the diameter, what is the length, what is the material, and that sort of thing. So this is the table of the different options that you have available to you. And so that's just a quick read of how you look at a specification like this for a fastener. There are specs like that for all the different fasteners that you might use, nuts, washers, nut plates, etc. So it's a good idea to get familiar with those, especially the ones that you use most often, and have those readily available. Read through them, understand what the typical geometries are, how to read the specs, etc. And that'll help you with the design of your fasten joint. So I know this has been a very quick overview, and this is only just kind of scratching the surface of how one does structural design work, but it just goes to kind of show you the general details that need to get worked out when it comes to designing a joint like this. And we haven't even touched on the structural analysis aspects of that. This is purely just how do you select the fasteners, what are the properties of different things you need to worry about and think about. But it's definitely a topic that can use more discussion. So if this is something you're interested in learning more about, reach out, put some notes in the comments, and feel free to send me a message and we can talk further. All right, well, hope you enjoyed that, and try and get some more videos out for you on other topics that I would think might be useful for aerospace engineers in the future. But until then, we'll talk to you later.